Okay, thank you. So I'm just going to spend like one minute introducing myself. So I'm a climate scientist at NIWA, which stands for, sorry, can you hear me? Yeah, National Institute for Water and Atmospheric Research. So I'm based in Auckland, New Zealand, so a long way from Austin, and a few hours as well from in terms of time zones. And at NIWA, I'm involved in both operations, like especially seasonal forecasting, and also kind of blue sky fundamental research, especially trying to reconstruct the climates of the past. And yeah, as I said, I'm a reformed MATLAB and R user, and actually, as an aside, I'm a reformed more than MATLAB and R user, because when I started my PhD in the late 90s, so everyone in my lab was using MATLAB, so I had to use MATLAB. But unless you've got thousands of dollars, and if you wanted to do a bit more statistics, you have to turn to R. But R is terrible to deal with relatively big data sets as the ones that we are dealing with in climate sciences. So you had to turn to various different tools. So all that made for a pretty messy affair, and also not very reproducible workflows. And but now with the Python scientific ecosystem and IPython and the IPython notebook, you can basically do everything from within the IPython notebook. You can do your whole workflow from data processing, data analysis, statistics, and visualization in Python. And I think that's a great thing. And I hope that more people in my field are going to move towards Python and the Python scientific ecosystem. So that was just like an aside. So I'm going to talk today about two very little projects trying to deal with very different actually problems. So just disclaimer, those are very new projects. I only started to push some codes for the first one, Clyesk, on GitHub a few weeks ago actually, and the other one is working, is running on our server back in New Zealand, but I need to refactor a lot of things before people can actually make use of it. So if during this talk you see something that could be of interest for you, or if you want to contribute in some way, or especially if you've got suggestions and comments, I invite you to come talk to me, or use those mediums to get in contact. So the first project that I'm going to talk about is called Clyesk. So that stands for Climate Data for the Environment Service Client. So that's a project that's been running for a couple of years actually, but not the Python aspect. And it's been developed initially for the Southwest Pacific region. So as you may know or not, so New Zealand is in the Pacific, and we've got strong ties with many Pacific Island countries. And Pacific Island countries already are very affected by climate variability, such as variability caused by the El Nino Southern Oscillation climate phenomenon. And they're also expected to experience major impacts from climate change, especially in terms of sea level rise and increased in rainfall extremes. So in that context, making sense of hydroclimatic data, local data, looking back at the past, knowing what's happening in real time, and better understand the forecast is kind of key to successful adaptation strategies to climate change. And this concept of making sense of data and deriving data analytics and visualizations has been kind of formalized by the World Meteorological Organization in the context of this global framework for climate services. Anyway, the important point here is that if you take a few keywords, you've got data, statistic, visualization, then you think Python, okay? So I'm going to dig a bit more on that, just so that you understand better the physical infrastructure. So that's of this project. So that's an example for Samoa, which is in the Pacific. So you've got those weather stations and climate stations. You've got also sea level recorders plus hydrological stations, and all this data is captured in real time across the country, across Samoa in this case. And the second step is to stream this data, to basically transfer the data. So there's an intermediate layer here. So an intermediate server which basically captures the data, and usually the data is transferred by the cellular network to this server. And there's a first layer of quality control in this case, and setting up alerts, etc. First level of administration, and then you've got the data is then transferred into Clyde, which is a PostgreSQL database. That has been developed by the Bureau of Meteorology in Australia. And as it stands, Clyde, so this database is relatively widely used in the Pacific to manage hydroclimatic data, because that's free and open source. But as it stands, this only allows very limited interaction with the data, and you cannot easily develop visualization and data analytics workflows in Clyde. So the goal of this project, the goal of Clyesk, was to build an application layer on top of this database, which again is widely used in the Pacific, that allows the development of tailored climate services. So one of the few requirements: it must be free, it must be open source, and open source is the obvious choice, not because of the philosophical underpinnings of the open source movement, but just because of the sustainability. I mean, many countries in the Pacific are countries in development. They cannot afford expensive license fees, etc. So open source is the key to having a sustainable system. And also, right from the outset, it needed to have the potential for local people to develop their own tailored climate services. So it needed to have a potential for local capacity building. So historically, the services, the scripts basically that are producing the outputs have been written in R, and have been pulled into the project a few months ago. And I thought, well, we can do some pretty cool stuff in Python, and thanks to the Python scientific stack and the Python scientific ecosystem. So I've been brought up into the project to develop climate services in Python and to develop this aspect of Clyesk. General view of the architecture. So you've got, so that's a web app, okay? So you've got the Clyesk web system, the front end, that basically handles all the, product requests from the user, etc., and manages all the display of the products. So you've got, again, the Clyde database is holding the data, so that's the data store. And the front end is just pushing the requests to a library of scripts that are written then either in R or in Python. And Python is then calling some specific modules that we've developed to analyze the data. And the products is pushed to a cache, and then the front end is pushing the products to the user. And we're interested in that, obviously. That's SciPy, so that's the Python component of Clyesk, which again is very new. So we rely on a few things to make people's life easier, so people on the ground, the people at the meteorological services. We use the Anaconda Python distribution. which provides the all the scientific ecosystem for free. We rely also on the PsychoPG2 library, which provides a connection to the database, which again is a PostgreSQL database. And on the server are installed some additional libraries that allow the development of relatively high-level data analytics and visualization, such as Vincent, Folium, and Seaborn. So I'm not going to talk too much into the details. If you're interested into the Python scientific visualization stack, I invite you to go to this talk. So that's from Rob Story, who's developed basically the Vincent and Folium libraries. Okay, so right now as it stands, the Clyesk Python component, there's one component which is called Clyde, which provides the interface to the database. So in this module, basically you've got a few functions that parse the script's arguments, request data from Clyde, and returns pandas data frames. And the utils module basically does a few things. As I said, there's several steps involved from the weather station to the Clyde database that include some kind of quality control with setting up of flags, etc. But a lot of things go through this quality control layer, and still the data that we get, even in the pandas data frame, is still messy. There are outliers, there are missing data, there's also missing indices, missing timestamps, etc. So utils provides a few functions to sanitize and clean up and reindex the pandas data frame, etc. There are some aggregation functions that handle a minimum number of missing observations, etc. Calculation of climate normals, standard plotting functions, etc. So that's a library of functions that allow the user to plug in different functions and to create their workflow and analysis and visualization functions. And then the scripts themselves, which are the services, are contained into a country folder, which is referenced in the Clyesk database. So that's the database with which the front end is interacting, and each country has a folder, and that holds a few country-specific files, such as shape files for plotting, etc. And the ambition is really to develop a library of scripts that are freely available for everyone to download, so for mainly of interest for the National Meteorological Services in the Pacific, which are using Clyde, and also commented IPython notebooks example. So that's and that tries to answer to the need for capacity building into the region. Okay, so I'm just going to show you quickly what it looks like. So that's the login page. So you can either log into Clyde, the database itself, for all the administration of the database, or Clyesk, Clyde Climate Services. Okay, you've got an about page, and then you can generate new products. So all those products are basically referenced to scripts that are running in the backend. One of them is, for example, a fire weather index. That's 5 minutes. And you can easily create new products in the Clyesk database. Okay, so that's one example. That's a real-time monitoring of rainfall. Another example, which I'm not going to show, is creating interactive maps using Folium. So very briefly, I'm going to talk about Picket, which is another climate web app, which was developed to answer some paleoclimate, reconstruction of paleoclimate problem, basically. So in short, in paleoclimatology, if you want to go back in the past, you have to use proxies, which are basically physical records that preserve information about past climate conditions, but also contains information about large-scale climate modes of variability, etc. And there's a kind of approach that we've developed with colleagues at NIWA, which use the concept of weather regimes, attractors in the climate systems to provide the link between local climate conditions and large-scale climate modes. So if you're interested into the approach itself, there's this paper, which you can download. There's no paywall. And the goal was basically, with Picket, to make this method available to other paleoclimate researchers who have limited or no coding ability or no programming experience, and also to foster collaborations within New Zealand and abroad. So again, a brief look at what it looks like. It's also login-based. You can enter your proxy. So the proxy details, what kind of proxy, what sensitivity it has, etc. Obviously the coordinates of this proxy, where this proxy has been recorded, etc. And then you end up with a library of proxies, proxy records, which are curated, etc. You can edit them, delete them, etc. And then you can get some diagnostics using this concept of weather regimes and climate analogs. So first for single proxies, so if you're interested in two reconstructed climate conditions associated with one proxy, but more interestingly, you can make multiple proxy reconstructions. So basically you have an ensemble of proxies, which obviously stabilizes the signal. And you can, start doing neat things like looking at global scale patterns of changes in the frequency of weather regimes associated with your ensemble of proxies. And so I guess I'm coming to an end. I just want to re-emphasize again that those two projects are very new. I'm not a computer scientist. I'm not even a good programmer. I'm only getting started with version control systems such as Git and GitHub. So there's a lot of training in best practice in scientific software development that is needed. So I really want to connect with the people who are behind the software carpentry initiative here at SciPy. I'm also starting into documenting all those modules with Sphinx. The goal going forward is to distribute those packages using Conda on Beanstar, and there's a few scientific goals as well. And one of them, for example, for Picket, is to extend this beyond New Zealand and make it available to other people elsewhere. And that's going to be through the implementation of a clustering tool, basically to extract those weather regimes, so people can select, their domain and extract the recurrent weather regimes for their region. And that's it. Thank you.